Okay, I want to talk to you in another demo about equilibrium. This is a big topic that we need to be considering in any kind of structural engineering. Equilibrium, in the sense we're applying it now, basically means the structure is not moving. If you build a bridge or a building, you don't want that building and bridge moving on you or bending more than allowed amount. So we have some conditions for equilibrium, and they're on your screen now. This is actually in your Project Lead the Way curriculum. If you look down under the links to get further down in your list, you'll find one that talks about statics and then equilibrium within that. Equilibrium basically means it's not moving. In this case, there are really three conditions to ensure equilibrium is happening: that the sum of your forces in the x and the sum of the forces in the y direction, or your translational motion sideways and up and down, is zero, meaning it's not moving in that direction. And then also your rotational equilibrium, the pivoting about a point due to a moment, that is also equal to zero. So I'm going to show you these. We're going to take these three conditions for equilibrium and we're going to apply them to analyze the forces and reactions on a typical beam. The beam is the basic building structure of anything that we build, because then from there you can make trusses and other complex structures. So if you'll take a look here at this basic beam that I've drawn over here, I put on the left side what I call a pin, and the pin means it's constraining this beam from moving left and right or up and down. So it has two reactions. It has the AX component, which restrains it in the X direction, and the AY component, which constrains it in the vertical direction. These are the normal forces. These are the reactions we talked about when we were actually doing free body diagrams. And also over here, I put a roller, and the roller constrains it from moving up and down. It will not allow it to move vertically, but it will allow it to slide side to side, which is typical of an expanding structure when it's loaded or gets hot. So we only have one reaction at the roller, and that's a vertical component, By. So point A, point B, you've got two reactions over here resisting the loading, one reaction over here resisting the loading, and our load is actually, if you ignore the weight of the beam at this point, our load is actually the force standing on the beam of 100 pounds. So what I want to do is I want to show you it's important that we calculate with that load on the beam, because this could be 1,000 pounds or 10,000 pounds. We want to know what is the loads going through these reactions at the connection points, because that's typically where you're going to have failure at, is in the fasteners. So we need to know what the load is there, or the reaction. So this is a three-step process. We first of all start at the pivot point over here at point A, and we sum up the moments that they have to equal zero. So I'm going to sum all of the moments that are occurring about point A. Well, since the formula for moment is force times perpendicular distance, AX and AY are zero distance from this point, so they produce no moment. Your distance value would be zero for AX and AY because they're going through the point. So AX and AY do not produce a moment. The only two forces that produce a moment here, and in this case, I'm not using the center one. I'm actually going to slide this load a little bit to the right, and I'm going to put it closer to the side B. It's only going to be 4 feet away from this point on a 16-foot beam. So we're going to see what happens to the load if you shift it a little bit off center, and how one will be loaded more than the other. So I'm going to sum all the moments about A. So this force out here, let's start at the one on the far end. By is actually creating a moment about point A because it's vertically up and it's 16 feet away from point A. So that's a moment of the force By, represented by that vector, times its 16-foot distance away from point A. It's a positive moment because it tends to bend it in a counterclockwise direction, And so we're going to label it plus. The other moment producing force on this beam is the 100-pound load coming down, and it's going vertically down. So it's going to be producing a negative moment or a clockwise moment. And so these two are going to balance each other out basically in a equilibrium condition. So that moment for that force coming down is going to be a negative moment, so we'll make a minus. It's 100 pounds, and we know from 16 minus 4, it's 12 feet away from point A. So we know from conditions of equilibrium that the moments have to total 0. And so now with a little bit of algebraic manipulation here, 100 times 12 is negative 1200. I'm going to move that 1200 to the other side by adding it. So I'm going to rearrange the 16 and the by. So it's going to be 16 times by equals 1200. And then, of course, all you would have to do at this point is to take the 1200 and divide it by 16. And so you're going to find out that the load at by is 75 pounds. So if you want to, at this point, you can go back up and label what you know in the problem. You've now, using the equilibrium of moments, you've actually solved for the reaction by, and by is 75 pounds from the 100-pound load up above. The second stage in solving an equilibrium problem is to sum the forces in the y direction. So I'm going to sum the forces in the y direction. So every vector that's vertical, up or down, I'm going to add it up, and this time I will include the a vectors because they're not canceled out in summing the forces. So we have a vector going up positive, that's ay. We have a negative force vector coming down, and that's 100 pounds, so that's going to be minus 100. And now we have a vertical vector by that's 75 pounds going up, that's positive. So we're going to add that, and we know from the condition of equilibrium, the sum of the forces in the y direction all have to equal 0. This is a very simple problem here to solve. If you put those two together, that becomes negative 25. And so if you move 25 to the other side, you'll find out that the reaction at AY is only 25 pounds. And this makes sense because you have shifted the load closer to B. So B is going to take more of the load. It's going to have more of a reaction, and less of the load will be handled by AY. And so we can label now AY is 25-pound reaction. And just for completeness sake, because in some situations when we get into trusses, we will have an X component to these loads. So you finish your equilibrium check by doing the sum of the forces in the X direction. And these are where you look for all the vectors that are horizontal, left and right. But we only have one, and that's AX, pointing to the right, meaning it's positive. And so AX is the only force in the X direction, and we know from the condition of equilibrium that the sum of the forces in the X direction have to equal 0. So we set AX equal to 0, and we're done. So in this condition here, the way this beam is loaded, AX has no load, and AY reacts with 25 pounds, BY reacts with 75 pounds, and when you add these two together, 75 and 25, you get an upward normal force equal to the downward weight of the force, and that is basically the solution of an equilibrium problem.